Okay, good morning, everybody. Thank you very much, Dee, for the nice, interesting introduction. Thank you very much. Thank you, thanks the organizer for inviting me to this very interesting workshop. I was also puzzled about the title a little bit. I did my search online. I say, well, why not? It's a good topic to discuss, and I hope I will show you in my presentations enough pros and cons facts that could support one or the other one. I think in medical robotics, the problems are even a little bit more complex, because we need to use machine learning, sometimes collaborating with human operators, sometimes just go autonomously. So what exactly will be the final solution is not very clear. And what I would like to highlight in my talk today, how this machine learning, possible application for machine learning, could enable safe and or autonomous manipulation in medical robotics, because we could have different applications. And I don't have a final answer. I think it's a research field. I think we have to push more to give some enough trust results such that we could make a decision. Okay, thank you very much. Sorry for the technical problems. My field of research, it's robot-assisted vitreoretinal surgery. This is a kind of microsurgery where the human skills are at the limit of human capabilities. And here in this video, you can see if the video is working, is not working. There are some problems with retinal surgery, and some of these may be related to the hand tremor, some may be related to lack of force feedback.
Sorry, I just want to close that up there.
Sure.
If I can find it. Where are we? Oh, here we go.
So what I try to highlight in red, there are areas where we as engineers, we could help the clinicians to solve such a kind of problems. And sometimes, are you sure this is working? So as you can see here worldwide, a lot of teams are trying to build robotic systems to assist retinal surgery. And I just display here some of the systems. They are definitely more. At Hopkins, we build a steady hand eye robot that is a cooperatively controlled robot. Where the clinician and robots, they share control of the tool. Unfortunately, one problem is we lose a tool-to-tissue interaction. And this is definitely not very pleasant for clinicians. What we try to do, we try also to develop force sensing tools using optical fiber technology, fiber Bragg gratings. And here you can see specifically a tool that we call dual force sensing tool, where we have active, we have force sensing capabilities as a tooltip, but also outside of the eye as sclera, and we could measure the tooltip force, we could measure insertion depth, and also we could measure force as a sclera. And I was trying to show you how it's possible to use this kind of technology. Here we can see my student Ali Ibrahimi playing with iRobot. And once the tool shaft is in contact with the sclera as the entry point into the eye, we measure the force. And once the force will go beyond level, we are able to change the direction of the force trajectory to keep it in a safe range. And as you can see here, it's obvious that the robot is doing its work. You know, we have an exponential function, and we set some safe limits before going to that maximum limit. The robot will, the system will identify the force and automatically change the direction. So this is a video with which in Montreal we got the best paper in medical robotics award. The video is fun, moves the eye around. The robot, the force sensing tool will detect the interaction and control the robot to keep in a safe range insertion depth, but also force as a sclera. Obviously, a tooltip wasn't important here. Well, is this a good application for technology? It is, because we are able to deliver, you know, the safety. What happens if the human operator will make a mistake? So are we able to detect that possible mistake? Are we able to predict? Are we able to compensate? Okay. So this is why I think machine learning may be a good solution. And as you may be aware, I'm not expert in machine learning, but my collaborator, Marin Kobilarov, is, and working with him, we are trying to see how to do this. So basically, Chanyang, he used machine learning, trains a network, collecting all the data, force information, insertion depth, robot kinematics, and do the task. It was basically, we call vessel following. When you insert the tool into the eye and using a microscope, just try to follow different vessels. And he worked a lot, collected data. And our network is able to give us a feedback if the force as a sclera is safe or unsafe. Based on the prediction time, I'm talking about what will happen in the future. Based on the prediction time, we take a decision to use a system to move on top of the human operator or just inform the human operator such that the human operator will take action. So, and here you can see an example. I think it's supposed to be a little bit sound, where the system, when the force in the future will be at a more than a specific safe level, it will send an auditory feedback and the user will try to compensate. Obviously, we are able to do this only for the sclera force. We have a second variable here, insertion depth, but because there are two different signals, I don't think the human operator will be able to react correctly. And after we tested in the lab, we ran some experiments with multi-user, and we showed that the system is working. So basically, in this case, the prediction was done 250 milliseconds in advance or 500. Obviously, here, how precise is the prediction is different. But no matter what, the system was able to catch, the possible mistake, give signal to the user, such as the user will react and compensate for the force. And here we can see some results. You see, everywhere when we are using that AICF system, all the metrics, they are very good, except that one where the blue line is actually the manual, and that is where the time for using the procedure is more. Also, we asked the users, so what do you think about this? And they didn't like. Okay, so again, the system is doing what is supposed to be done. The system could inform the human operator what to do, but still they don't like too much. And here you can see also some examples. So those users, they were people without any training in robotics. Here we have 3 users, experts in using the robot. And in this case, experts in surgical procedure, in experts in robots, in this technology is good. More than that, we see a level of results when using the system where the robot will help the beginner to get the same results with the expert. Okay, so again, this was machine learning used for the control when the system has to collaborate with the human operator. When the human operator wasn't able to react in real time, the system took action on top of what the human operator is supposed to be done. Moving on, we are trying to see if we can use this technology for other kind of procedure. And one idea was to go with a bilateral approach. And we try first with a system for automatic light pipe, where basically a robot will move the tool while a second robot will try to follow the tool and maybe shine the light. Now, in this case, we didn't use basically machine learning. This was based on regular registration. We set goals for the robots moving the light pipe when the user are still using the dominant hand tool for moving the tool. The results are, I think, very good, and it looks like it's possible to do the job without machine learning. Other idea was to see, okay, it looks like we could use a robot for moving the light pipe. Now, in that case, we could still use other two robots to do a procedure and have a third arm to illuminate what we are doing inside. So this is why we come up with this bilateral cannulation. The idea here it was to use a tool to stabilize the tissue, the vessel, and after that come up with a needle to insert during the procedure. And as you can see here, yes, you see there are two robots with two dual force sensing tools, and Chanyang is even trying to move the eye manually. The robots are able to move around. The forces as a tooltip in safe range, forces as a sclera in safe range, insertion depth in safe range. So it looks like it's working. And we try to move on also to do some robot-assisted bilateral vein cannulation. Obviously, in our eye model with vessels made by rubber tubes, it's working nicely. We are trying to see if that is also will work in a real eye. So moving on, we try to use machine learning for autonomous guiding the tool motion inside of the eye. This is an work done by Brian Kim, and here you can see the diagram. And this is where it's the image that actually Dee used for his presentation, where this is in open sky, eye model made by rubber, and just go there, identifies a top-down, in top-down image, identifies the target, and the robot will go and touch that target. It looks like it's working. Here you can see also basically on the left side that the system is robust enough such that will do the targeting even we have another tool coming, in that field of view, or if we like to do vessel following, just identify trajectory points around the vessel and after that insert. We could use this even more. For example, in this case, it's a kind of registration tooltip to retina. Basically, if we assume that you know the size, the shape and size of the eye, and we identify where the insertion sclerotomy point or remote center of motion point is, we are able also to basically reconstruct the retina surface. That was done on a plastic eye model. We are trying to see what happens if we go with more realistic cadaveric pig eyes. In this case, we try also to do some vitrectomy for the eye. And as you can see here, could you see if it's... okay, so what you can see here, this is the same application in a cadaveric pig eye. visualization to the microscope after vitrectomy. And it looks like it's still working, and we are even trying to mimic the eye motion drift. So in that case, the system is able to we add a force sensing tool, so the system is able to compensate for that motion, and after that still go to the target. And because we are assuming that the RCM it's enforced, we try to measure with a force sensing tool. And here we can see some results. So those are results from 10 trials. And the forces are in range until 20 millinewtons. That is a small force as a retina. In our experiments was a human will do in manual procedure, it's around 130, 140. And you can see here a variation for manual, but this is not for an expert user. Now also here you can see that when the eye will move, the system is able to catch the movement, and after that compensate for the movement. And you can see this also in the variation of the sclera force. Basically, it's working and it's safe. Okay, as a last application that it's ongoing, hey, my friend. So we are trying to move on and to use optical coherence guidance for retinal surgery. Basically, with a video camera, microscope, or whatever, you don't have enough resolution. Our goal is to go in subretinal space. Our space to insert is 300 microns. We need something that will give us 5 to 10 micron resolution. This is optical coherence tomography. And what you can see here, we are trying to combine, interface our system with a microscope, get real-time information from an OCT, and after that, guide the robot. If our paper at ICRA is accepted, we will show you how we did it. Okay, these are my conclusion. It looks like we have to do a lot of work to enhance and enable safety. Definitely, machine learning it's a solution for this. With this, I'll conclude my talk, and I'll be more than happy to answer your questions. Thank you very much.
Thanks, Dr. Iordachita, for the nice presentation. It's question time.
Thank you for your very interesting talk. It was very impressive how you could compensate for the manipulation of the eye to keep the RCM, but also be able to keep the position inside the eye. So I was wondering how you do that. So the RCM is clear, you adjust for the forces, but how do you make sure that you still stay at the same position with the tooltip?
Yeah, so well, definitely in order to explain you better, we need to take a look at the paper. So before we prove that with one tool, force sensing, dual force sensing tool, we are able to get information, real-time information, sclera force, insertion depth, also how we measure insertion depth I could show you, and after that tooltip. And basically, once we try to control everything, we just get the force, insertion depth, and tooltip force information as conditions for control to control the whole motion. So it's an optimization problem, but it's working. It's a little bit tricky, the tooltip, because once we have to catch the contact point. And in that case, the sclera force insertion, that is easy because we have continuous signal. But once we go as a tooltip, that means to get the first force and after that try to lower that. What we did, once we are, because we know the insertion depth, once we are close to retina, we slow down the motion.
Okay. So,
again,
but
it's just a very short answer.
Yeah.
The answer is a little bit longer.
Thank you very much.
Yes. Yes, please.
Thank you very much. Amazing work. So I'd like to ask, because there's quite a lot of work here presented in vitreoretinal surgery, robotic research. So my wife is eye surgeon, but more like glaucoma / cataract. So we were thinking whether there is something going on around this in this scope. Are you aware of both robotic and machine learning?
Oh, you are talking if there are applications for cataract?
Yes, whether there are any robotic or machine learning applications, interesting applications in glaucoma or cataract.
Sure. Well, there are very good results, and in whatever. So this is, superior part of the eye, inferior part of the eye. Inferior part of the eye, retina is very, you need very skills. You need also good skills are cornea, but is considered a little bit easier. This is where actually people are pushing for autonomous procedures, and. Yeah, I don't know. Brady Nelson, for example, Professor Nelson, he already have such a kind of system. Even Professor Isaac from Duke, they have a OCT guided robot for cornea, and there are also other applications that people are trying to do this more or less autonomous, but there are, and they are working pretty well. The problem is this such a kind of work. The cataract, it's a very short procedure, and basically it's there are minutes. So the robotics cannot compete very well with human operators because they say, why do you need a robot for that? But we are engineers, we like to, challenging scientific challenges, and we will solve also this.
So thank you very much. So I'll just add that I developed a cataract simulator for training, which was licensed to Alcon actually. So I was thinking to use it as a research platform for machine learning for like cataract surgery at some point. Thank you.
No, so we talk with a company if this technology we are developing could be used also for such a kind of training systems. And that may be the first actually step where we could advance use the technology as it is, because that is not in clinical application and it's easy to sell. Yeah,
thank you very much.
Yes, please.
Thank you for the very interesting talk. I was wondering, you talked about two separate types of robotic intervention. One was the robot will do like a buzzer or something and let the surgeon know that they're inserting too much force or maybe going somewhere they shouldn't. And the second type, you said the robot actually takes action. I was wondering, in the second case, when the robot is taking action, do you see that the robot will just stop and like stop the surgeon from doing something, or will they actually be taking like, I call it like active action to move? And if that's the case, if they're taking active action, how does the handoff happen back to the surgeon?
Yeah, thank you very much. I tried to show a slide where it was a control diagram. When we attach the tool to our robot, there are 5 degrees of freedom. And with our, once we control the tool motion, the robot could control 1, 2, or 3 degrees of freedom, and the human operator will control the other 2. So again, the human operator will control the robot. Once we think that the robot should take action, it will act in parallel with human. And basically, the human is still able to move the tool, but some direction are restricted. Okay, so in that case, we enforce the safety for some specific directions. Still, the human operator is able to do something. Now, how much freedom we have to give to the robot, that is a research problem. And you like the robot to do something without the human operator to feel the restrictions. There is also another question. If something happens, who is in charge? I don't think we are able to answer to this question now. Again, it's possible we control only some specific degrees of freedom. Everything is done in parallel. Once the safety is not anymore a concern, the robot will return the full control to the human operator.
Thank you very much.
So I'll be more, please. The last one, we could discuss after that even more.
Thank you, Professor, for your next presentation. I'm wondering, do you have any insights on fusion the OCT data with the FBG data to provide a more safe manipulation for eye surgery?
Okay, well, there are two problems. First of all, you need to get a real-time OCT data.
Right.
And after that, getting the force information data in real time. Now, we are able to get the force information. OCT data for now is not possible. I show you a system where we got from Leica a piece of software that will allow us to stream the OCT. Unfortunately, it's still 3D, so it's not real time. But we build a system custom-made where we get B-scan that could be real time, and we are able actually to combine them. It's still work in progress, so I don't think I could show you a proof that force information and OCT information is the same time it's working. I show you one where microscopy and force information it's working. We have separately OCT with also microscopy, but not combined. But I think this is what we are planning to do in the future.
Thank you, Professor.
Okay.
Thank you for your talk. Do you think that model predictive control techniques can still be usable in these applications, or do we need to rely more on machine learning?
Oh. Well, it depends on how complex is a task that you are trying to model or whatever you do. But I think for a simple task, it may be okay. For more complex problems, it depends on what are you trying to do. We are trying to combine a model with machine learning in needle shape sensing, where we have a model for what is supposed to happen, but some parameters of that model we learn by machine learning. Because yesterday in the session where Professor Emmanuel van der Porter was chairing with Professor Paulo Dario, it was somebody from Jessica Brunner where they these flexible tubes, you know, and somebody asked if we should use a model or should we use machine learning. Well, you need to have a model for whatever you have in that flexible structure, and potentially after that come up with a machine learning, because you still need to stay in what is physically possible with you know, with those flexible rods. So I think a combination could be also a good direction.
Okay, thank you.
Yeah, thank you.
Yeah, okay. I think then we can go to our next speaker. I know you have a lot of questions, but if you have questions, you can talk to Dr. Iulian Iordachita afterwards. And also from 12 to 13, we have a panel discussion. So you will see a lot of incredible conversations. And now we go to our next speaker, Dr. Paolo Fiorini from University of Verona. And his presentation title is Some Useful Use of Machine Learning in Robotic Surgery, the Finding of the ARS Project.